Okay, so this general form of this potential energy, this matrix element here contains 3n by 3n matrix elements because we have n sites, but each site we can have the lattice vibration along the 3 different directions, as I mentioned last time, right? Okay, and altogether this matrix is really big, which is 3n by 3n. So then we should come up with a clever idea to diagonalize this very big matrix and find the eigenmode and the normal mode and so on. So we need to diagonalize it, this 3n by 3n matrix, by 2 steps. So we should follow 2 steps diagonalization because of course we have 2 different degrees of freedom, right? So one is XYZ, another is the psi index. So we could step by step diagonalize this into 2 steps. So first one is to diagonalize this site index called site diagonalization. So for each say matrix element here, this is the 3 by 3 matrix, but each matrix element here represents the n by n, right? Remember that. So each is actually n by n. Okay, so we first we want to diagonalize this n by n matrix on each site by introducing this normal mode coordinate, and we still keep this at xyz, and the next step we would like to diagonalize the xyz, okay, the spatial coordinate. So therefore the first diagonalization involves only a y on site L and L prime, but then we transform this y L or L prime into the normal mode basis yq, where this xyz is still xyz in the first step of diagonalization. Okay, so as we did before, we first transform this yli, where I could be xyz, into the yq, and likewise this pli, this momentum operator, could be transformed in a similar way. This is the Fourier transformation. And of course we have a translational invariant. The translational symmetry indicates that this, if you shift your momentum variables of Fourier momentum variables q by a reciprocal lattice vector, you get back to this the same vector, displacement vector, and same for this momentum variables. So then we only keep the q variables within the first Brillouin zone, because we could shift this lattice vector, this q by a lattice vector, reciprocal lattice vector g, so that this this q prime is actually the same as q by a shift of amount of g, where g is a reciprocal lattice vector. So therefore we could always keep our momentum in the first Brillouin zone. So this is the value of q. All right, so then imagine that we could do that. Of course we have done that, right, in the one-dimensional case. And this is just a slightly more complicated situation, but we could do that pretty straightforwardly. So imagine we could accomplish this site diagonalization, and we could transform this PL to PQ. Remember that when we did this site diagonalization for the one-dimensional phonon case, after we transform this basis to Fourier variables, then those momentum variables are still canonical momentum variables, and the kinetic energy keeps the same form as p squared. But then we should really write down this most complicated term, this potential term, VQXX. Okay, good. So imagine that we have done the site diagonalization, and each matrix element in this 3 by 3 matrix represent n by n matrix, right? Where you have only non-zero matrix element along diagonals once you have done the side diagonalization, right? So each matrix element represents the diagonal n by n matrix that you already accomplished the side diagonalization, right? So the remaining job is to diagonalize the 3 by 3 matrix or 3n by 3n matrix. So then we take a short break, and when we come back, we continue the second diagonalization, which is the coordinate transformation that takes us to the so-called symmetry axis, okay, just like a rigid body rotation in your classical mechanics, right? So when the rigid body rotate, and to study the rigid body rotation, it is more convenient to transform your xyz coordinate to this rigid body coordinate, right? Okay, and therefore we need to make a coordinate transformation. So let's continue. So once we have done the side diagonalization, the remaining job is to diagonalize the 3 by 3 matrix, and this can be done following the similar procedure that you learned in classical mechanics, namely the rigid body rotation. Suppose this is a rigid body and it's a symmetrical top, right? Okay, so it could perform such a three-dimensional rotation. But suppose this is the symmetry axis that the rigid body rotates around. So to study this rigid body rotation, we need to really rotate the coordinate to the new axis, so-called x prime, y prime, and z prime. For example, the z prime represents the symmetry axis where the rigid body rotates about, and so you need to transform your xyz coordinate to this new, say, a rotated basis, so that one of the axes actually coincides with the axis of rotation or symmetry axis. And so this is the same thing here. So we need to perform such a rotation of a axis to the symmetry axis, and I assume that you have learned that in classical mechanics, so I don't repeat the procedure. But then at the end of the day, you will transform your xyz to the new basis called S1, S2, and S3. Okay, so along these three new coordinates, S1, S2, and S3, in this new basis, this VQIJ matrix element is actually diagonalized. Namely, you have only three non-zero eigenvalues along the diagonal directions, and all the other matrix elements are zero, because you already transformed your axis to the symmetry axis, so that along the symmetry axis, the 3 by 3 matrix is diagonal. And the three axes, S1, S2, and S3, are called direction of polarization of phonons. So we rotate the coordinate to the basis unit vector, S1, S2, and S3. And this three unit vector are called directions of phonon polarization, which means that the phonon propagation could actually go along the three different directions, new directions, S1, S2, and S3. So in 3 dimensions, we have 3 different, say, normal mode directions, which are exactly S1, S2, and S3. Then we label the eigenvalues according to their polarization directions, right? S1, S2, and S3, so which means that this harmonic oscillator potential term along the S1 direction takes the value of the VQS1, and so on and so forth, and these 3 eigenvalues are not necessarily the same. Okay, they can be different, which means that depending on your lattice structure, so the atoms may vibrate, say, in a different way along S1 direction with respect to the other direction, and so on and so forth. So we could just combine these 2 steps of diagonalization, and the Hamiltonian could be written in terms of a very simple form. So you sum over this Fourier variables q, or momentum, and polarization directions, right? So there are 3 polarizations. So you need to sum over both q and s. And of course, you could define such a, yqs and pqs in the same way that we defined those normal mode coordinates previously. So in this fashion, all these variables, say q and s, are independent of each other. Namely, the normal mode vibration for any different q's are all independent. For any different polarization directions are also independent. Okay, so you have 3n by 3n different normal mode. So let's just continue. So, but this both q and s are vectors, right? So q and s are 3-dimensional vectors along, in the 3-dimensional space. So we can have these 2 situations. S is parallel to q, which is called longitudinal. And when s is actually perpendicular to q, we call this transverse. So let me just define more clearly the meaning of this q and s vector. So q is actually the direction of this wave propagation, and s is the direction of vibration. So in other words, this q actually represents the momentum transfer, which is the direction of the wave propagation. Okay, so this, for example, the electromagnetic wave or light wave, they actually go in the direction where the wave propagates. Okay, so however, this s direction represents the direction of vibration. So this s, this lattice vibration can actually go along with the wave propagation, or can actually go perpendicular respect to the wave propagation. Meaning, this s could actually go a different direction or perpendicular direction respect to this wave propagation, or could be in parallel with the wave propagation. So therefore, we could distinguish these 2 different situations. When s is parallel to q, we call this the longitudinal phonon mode. But if s is perpendicular to q, we call this transverse. Okay, so let me just give you an example of what this transverse mode could mean. So remember your electromagnetic wave, right? Suppose your electric field is actually vibrate along, say, y direction, but then your wave propagating along the x direction. And this is the case where we call this transverse mode, meaning your lattice vibration is along one direction, but the wave is propagating along the perpendicular direction. Okay, so your atoms are moving like this, but then the wave of that vibration actually is propagating along the perpendicular direction. So we may have the this longitudinal mode where this lattice vibration coincides in direction with the wave propagation like this, right? So you could have such a kind of longitudinal mode or transverse mode like this. Okay, so we'll distinguish these 2 different modes for the later convenience, because in nature we can really find such a different phonon mode, transverse or longitudinal. So let me just generalize the dispersion relation for phonons in 3D. So we have calculated the dispersion relation for a 1-dimensional phonon, which is nothing but the absolute value of a sine function, right? And here we have very similar situation, except now, apart from this index s, the direction of phonon polarization, everything else is the same as 1-dimensional phonon. Okay, so you can consider this just a straightforward generalization of a 1-dimensional phonon. You just put s there, representing the phonon polarization directions. So you sum over 3 independent modes that phonon is polarized, or direction of lattice vibration along 3 different independent directions, S1, S2, and 3, and that's it. Okay, so you just need to put the extra polarization index S on one-dimensional phonon Hamiltonian, and you are done. Okay, so this is simplest generalization of physical systems from 1D to 3D, and we don't care about this complicated diagonalization procedure because this can be done. Okay, straightforwardly. So then we just assume that this is done, and you have 3 different polarizations of phonons. Therefore, you have 3 different oscillation frequency or phonon mode. You got 3 dispersions. And we know that the 3 different matrix elements, this matrix element can be different. As a result, you can expect that you have 3 different dispersions like this. So suppose this is omega q S1, this is omega q S2, and this is omega q S3. So you still restrict yourself to the first Billiard zone. Okay, so we don't know what this, which is which, but we know that in general there can be 3 different, say, dispersions corresponding to different polarization directions. And this is called first sound. This kind of similar to the sound wave propagation. The velocity of a sound wave is actually d omega by dq, and sound velocity is actually different along different polarization. Okay, so if, as I mentioned, we can have this longitudinal or transverse mode. Okay, suppose that we are in the longitudinal mode, and this S is actually along the same direction as Q, right? So this kind of a longitudinal phonon mode mimics the sound propagation. Okay, so remember in your classical mechanics, you know how the sound wave propagate, right? Okay, so the sound wave propagates exactly the same way as the longitudinal wave propagation, meaning your vibration of these molecules of air is along the same direction of that sound wave propagation. And therefore, people call this longitudinal phonon mode as just a sound wave, okay, because it looks very much like the sound propagation. So now we are able to second quantize this 3-dimensional phonon Hamiltonian. You know that the only difference here is that you have the extra 3 degrees of freedom attached to 3 different directions of a vibration, and other than that, they are identical to 1-dimensional phonon problem. So let's take a short break. When we come back, we'll just follow the second quantization that we have done for 1D phonon, and we generalize it to 3D phonon. And we will study a slightly complicated lattice called non-simple Bravais lattice, which is the kind of an interlocked Bravais lattice between the 2 Bravais lattices. And then we have 6 phonon modes in that more complicated situations. Okay, so let's take a short break. So let's second quantize this. As we have done for 1-dimensional phonons, we could define such a bosonic operator. But now we should differentiate different polarizations by attaching this polarization vector S to the boson field. And remember that this both Y and PQ are vectors, also quantum mechanical operators, but they are vectors. And we should dot it into this S vector here to actually get the 3 different components of this polarization vector. So the speed dagger. So after this definition, we second quantize the 3-dimensional phonon, just like before. So we only add the 1 more extra index S to the one-dimensional phonons, and we're done because we have 3 different polarizations. Okay, so nothing is surprising. So this is the simple 3-dimensional phonon mode on the simple Bravais lattice. But here we could generalize this to a slightly non-simple case. So in the non-simple Bravais lattice, especially in the special case of the set of interlocked Bravais lattice, which we label by L and Bi, where I is actually 1 or 2. And we have such a non-simple Bravais lattice. Suppose this solid dots represent the one Bravais lattice, okay? And you could superimpose another simple Bravais lattice, but shifted by vector Bi, and you'll get the new Bravais lattice, like this. And you could also connect these red atoms like this. So in other words, you superimpose 2 simple Bravais lattices, but shifted with each other by some vectors. And you could define a center of mass somewhere in the middle. So let me just define this, and let me just magnify this, zeroing this 2 set of interlocked Bravais lattice. And you can define the center of mass of this 2 interlocked Bravais lattice, and there are 2 vectors that connect to the 2 different sublattices starting from the center of mass, and this one vector is called B1, another is called B2. Okay, so you could define these 2 vectors B1 and B2 connected to the center of mass, which define this interlocked 2 Bravais lattice, and therefore you could define a displacement vector for a lattice vibration depending on whether this displacement is on the solid side or on the empty side. Okay, so on the solid side, since it is actually related to the center of mass by this lattice vector B1, so you attach this lattice vibration on the solid side, YB1, and likewise the displacement on the empty side is called YB2, and so on and so forth. So in other words, both YB1 and YB2 are 3-dimensional vectors. It can point to any direction along 3-dimensional space. So you have 2 more independent degrees of freedom added into a 3n by 3n system. So altogether, it's a 6n by 6n degrees of freedom, right? So in a simple Bravais lattice, in 3D, you have 3n by 3n matrix elements, but here you double this degrees of freedom, each of this, this column row direction, so you get 6n by 6n in total degrees of freedom. And as a result, you may have 6, say, dispersion relations. So 6 omega q, S and I, right? So S is the polarization vector, and I is actually sublattice indices. So you have twice as many dispersion relations as in the 3-dimensional simple Bravais lattice case. So, but let's just do the simple algebra. We generalize this YQ BI in the same way that we have done already many times. So then this VQ BB prime is the Fourier sum LB L prime B prime IJ. Okay, so in other words, we could enlarge this matrix to include such 2 different say, sublattice structures of this non-simple Bravais lattice, and we need to diagonalize this in 3 steps. First, the side diagonalization, and the second is polarization directions, and of course you need to diagonalize the sublattice indices, but we pretend that we have done that. Okay, so the full Hamiltonian is simply just one more index compared to the simple Bravais lattice of a 3-dimensional phonon. So let me finish this. So there are 3 MB degrees of freedom, where MB is a number of atoms within a unit basis. So MB is actually 2 for this 2 sublattice structure. Okay, so then we could plot 6 branches of this phonon dispersions, and we'll take a short break. When we come back, we will classify all these 6 phonon dispersions, and we called the lower energy, say the lower 3 branches acoustic, and the upper 3 branches optical phonons. Okay, so let's take a short break. Okay, so let's continue. So as I mentioned, this interlocked non-simple Bravais lattice shows 6 phonon modes, and 3 of them are lower in energies, and another 3 are located higher in energies. As Q goes 0 limit, the lower 3 modes are called acoustic phonon, and the upper branch 3 phonons are called optical phonons. So let's just study why are they called acoustic and optical respectively. And in fact, this kind of a normal mode vibrations in such a 6 phonon mode per Q value can be shown to have different kinds of relative phase with each other between this empty side and the solid sides. For example, this acoustic phonon, which shows that the low energy branch, in fact, are the so-called in-phase oscillations. Okay, so the in-phase oscillations refers to the fact that both empty and solid atoms are moving together. There's no relative phase or relative motions between the empty and solid atoms, so they move together, okay, like this. So when they oscillate together. Okay, so the empties and solid sides are in-phase oscillations, and such an in-phase oscillations is known to carry lower energy. Okay, because they, from this classical electrodynamics, you know that this energy associated with in-phase and out-of-phase are different, and in-phase oscillations always carry lower energies than out-of-phase, where this optical branches of phonons are exactly this opposite situation, where the empty and solid atoms are moving against each other. Okay, so they are out of phase, okay, by a phase pi difference, so when this empty sides actually move downwards, the solid sides are moving upwards, so they get opposite way of oscillation. So therefore, this out of phase oscillations usually carry higher energies, and that explains why there are 3 branches above and 3 below. But why are this high energy mode called optical mode? So let's just study. And why are this in-phase mode called acoustic? All right, so this connects to the earlier statement that you have this longitudinal or transverse type of motion. So let's look at this acoustic mode first. Suppose I just look at this lattice vibration along any directions, and especially this acoustic phonon mode, where the atoms are moving in phase. Okay? And such in-phase oscillations could be illustrated in this cartoon picture where the plus and minus side refers to two different charged atoms, for example, and then they actually move together. Okay, suppose this plus side refers to the, say, the solid side, and minus refers to the empty side. So both plus and minus atoms actually are moving together in phase. Okay, but then the wave propagation is kind of sound wave propagation. It's actually along the same directions. Remember, this is the direction of K or Q, where Q refers to the wave propagation. So this wave propagation is along the same direction as the lattice vibration. Okay, so this plus and minus sides actually move like, back and forth like this with associated amplitudes, and then this wave propagates along the same directions as the vibration of the underlying lattices. So therefore, this S is actually, parallel to Q, and this is a longitudinal, and it's a sound wave-like propagation. And that's why we call this acoustic, because this word acoustic refers to the sound related. And as I mentioned, this in-phase oscillation costs lower energies, and that's why they appeared in this lower branch of the 6 phonon modes. And because they're longitudinal phonon propagation, and we call them acoustic phonon. So let's look at this optical. So for the optical mode, things are very different. So because this plus and minus side, or empty or solid sides, move against with each other. So you can very clearly see that there is electrical polarization between the plus and minus side, because these two atoms are moving like this, okay, when they propagate. Okay, so therefore the propagation direction is actually perpendicular to the lattice vibration between this plus and minus sides. So therefore, in this many materials, solid-state materials, there are two sublattices, exactly like what we just studied here, that we have interlocked two Bravais lattices, and then these two sublattices refer to most likely this positive ions and negative charged ions. So there is an electrical field pointing from this positive sides and negative sides whenever they oscillate. Okay, and this is the origin why we call them optical, because the electromagnetic wave is actually a light wave, and optical refers to the physics of light. Okay, it's an adjective which describes light-related phenomena, and because of this electrical polarization, we have this optical properties of this phonon mode. And as I mentioned, in many cases, the out-of-phase oscillations often cause much higher energies than the in-phase motion, and that's why all the three optical branches phonons appears above these acoustic phonon modes. So these acoustic and optical phonons are very common properties of solids when we study this phonon mode, and they usually appeared when you excite this, or when you study the final temperature phonon contributions to the say specific heat and so on, and you'll find that there's two different normal mode vibrations, and so we call this a transverse mode, and for the optical phonon, and longitudinal phonon mode for the acoustic phonon mode. Is that clear? So I guess that's the end of the introduction to the phonon dispersion in relation to the coupled harmonic oscillators. If there's no further questions, let's continue studying the the thermodynamics of this phonon. Is there a longitudinal? There may be some mixed modes, but I doubt you will find this mixed mode. Okay. Right. So either they move along the same direction, or they are perpendicular to each other. So, well, I guess this, whether there's some mixed modes will be decided by the dispersion eventually from experiments. Okay. So you can clearly see this two different groups of this phonon mode. Okay. So the lower three really connect to zero. Okay. So we know that this acoustic phonon mode will hit zero when Q equals 0, because this is what we already derived for one-dimensional phonon. Okay, and so you can really tell whether this is really an acoustic phonon or optical phonon, or a mix between acoustic and optical by looking at this dispersion relations. If all the three hit 0, and there's no chance that they mix, because this is a characteristic of acoustic phonon, not a question. But of course, you may have different dispersions, and acoustic phonons may actually mix with the optical, which I don't know any examples of this. So you may have such some kind of intermediate kind of a phonon dispersion. I'm not aware of any example of that. Maybe there exists such a mode, but oftentimes you will see this. Okay, and I'm not just drawing this for fun. This is really what happened in the materials from the experiments. So they really observed such 6 different phonon modes, and 3 of them actually extrapolate to 0, and another 3 actually stay finite in the Q equals 0 limit. So this is the real phenomena, which may indicate that you may not find this mixed acoustic and optical phonon modes. Right? Okay. Good. So let's just look at the thermodynamics of phonon. So how do you actually see this phonon? Of course, you need some experimental help, right? So such an experiment could be designed from this tunneling event, so-called phonon-assisted tunneling. Okay, so you may just hit this tunneling barrier by some, say, electron beam or some neutron beams and so on, okay, and perhaps neutron beams. And then in the solids, you may, at finite temperatures, you may have such phonon excitations, and this neutron beam may absorb one phonon or multiple phonon energies, and with the help of this phonon absorption of phonons, this incoming particles gained kinetic energy, and therefore this could actually tunnel through the tunneling barrier, and outgoing particles carries a different energy E2, and this difference between E1 and E2 is the phonon energy. So it's much like what we have encountered before. Remember, from this plasma oscillations, you hit the aluminum thin film by electron beams, and then you observed by a detector the outgoing electron intensity and their energies, and difference between the incoming outgoing electron energies define this plasmon energies, right? So likewise, you could actually see this phonon contributions by this phonon-assisted tunneling experiments. So the probability to see this is actually proportional to the density of states, per unit energy times the energy windows delta omega, or frequency windows, which is the energy difference between E1 and E2 divided by h bar. And we will study this density of states, and then we could evaluate the thermodynamics properties of such phonon. And density of states, d of omega, is the number of states per unit area and per unit energy. And we will employ a model called Debye model, which is the approximated model calculations for phonons. Okay? And we will define what I meant by Debye model later, but let's just sketch what we would do. Okay, so what we would do is to evaluate the specific heat, which is the temperature derivative of the average energies, E bar. So E bar is the thermal ensemble average total energy of your phonon system. Remember, this H represents the Hamiltonian, and the Hamiltonian of this phonon consists only the kinetic energy and the simple harmonic oscillator potential, and in 3D. So at finite temperatures, we take ensemble average E bar by evaluating this, numerator and denominator, this, this partition function and so on and so forth. And once we've done this, to evaluate the E bar, we take the temperature derivative of the E bar, and we get specific heat or heat capacity at the fixed volume, and then all the thermodynamics come from the specific heat. All right, so remember this Hamiltonian is extremely simple. It's just a coupled normal mode vibration of a simple harmonic oscillator. Okay, so it's made of just 3n or 6n copies of independent simple harmonic oscillator. And we simply just need to perform the ensemble average of the total energy of your phonon system, and then following the standard statistical mechanics, and then we are able to evaluate. So now you can appreciate the second quantization approach, because remember, this Hamiltonian in the second quantized form is nothing but h bar omega qs times b dagger b qs plus 1/2. Okay, so what is b dagger b? So we mentioned this millions times. This is nothing but the number of bosons. And the number of bosons satisfies the Bose-Einstein distribution function. The finite temperature, when you evaluate this ensemble average, it is simple. It's nothing but the Bose factor. And 1/2 is just a constant. So it is a piece of cake to evaluate this ensemble average once we know, this second quantized forms of this Hamiltonian, and the remaining job is really simple. So if you don't do this second quantize, if you don't second quantize this Hamiltonian, and I don't know there's a way to calculate this thermodynamics of phonons. You may never discover phonon if you don't use the proper language, and you may know nothing about phonon. In the second quantized form, the Hamiltonian is already diagonalized, and it is expressed in terms of the number of bosons, b dagger b plus 1/2. Therefore, you plug in this Hamiltonian, and you get very simple form of the E bar, which is nothing but the sum over QH bar omega Q times this NQ bar plus 1/2, whereas NQ bar is nothing but the ensemble average of the boson number. And this is precisely this Bose-Einstein distribution function that you are dealing with, because NQ bar is the average phonon number at the finite temperature, which is precisely the Bose-Einstein function. So then we just plug in this Bose-Einstein factor here in the E bar, and we take a temperature derivative of this E bar, and you get CV. Right? Okay. So this CV involves the sum over all possible Q with this complicated exponential form coming from this Bose-Einstein factor. So how do we do this summation? Well, here comes the Debye approximation. So Debye said that, of course, we don't know exactly the density of states of the phonon is, but we can make some approximations. Because in reality, this phonon mode may have such a complicated density of states as a function of omega or energy. But we could fairly reasonably approximate this density states in a quadratic form, so that this the red curve is a Debye approximated density of states, which is proportional to omega square. Of course, this is approximation, but how good this approximation is, well, it turns out that this approximation is really good to model the thermodynamics of phonon contributions for different solid-state materials. And there's a cutoff energy or cutoff frequency beyond which there is no density of states, meaning the phonon contribute to the density of states of phonons, and at some cutoff frequency. So beyond that frequency, there's no density of states available here. So which is also in a good agreement with realistic materials that you cannot find the phonon density of states beyond certain energy or frequencies. And this omega squared dependence of the density of states is really the contributions from Debye. Okay, so let's just rewrite this summation and turn into integral. And we could further actually sort of qualitatively derive the Debye approximation. So this quadratic behavior of the density states of phonons comes really from this acoustic phonon branch that we just mentioned many times. So at low temperatures, the assumption behind this Debye approximation is that the acoustic phonon dominates all this low energy, long wavelength fluctuations, so that we can simply just take the, say, a linearized phonon dispersion, and we can calculate this phonon dispersion relation that will contribute to the density of states, and that contributions turn out to be exactly omega squared. So let's just recover this omega squared dependence of density of states. So as I mentioned, in the low Q limit, Q equals 0 limit, delta omega is actually proportional to delta Q, or omega is actually C times Q, where C is sound velocity or phonon velocity. Right, so you could easily get this omega square dependence on the density of states of phonons as functions of omega when you perform such a change of variables from this summation over Q to integration over omega. Okay, so when we do that, you know that when we do this change of variables, this volume integral should be conserved, namely this total, say, density of states, which is for this infinitesimal window of delta omega and delta Q, or infinitesimal difference in momentum Q. And if you multiply this d omega times d of omega, density of states, it should be identical to the same summation, but down in this Q space. In other words, these density of states should be conserved. Okay, so that's the essence of a change of variables. So the total density of states in this thin shell is the same regardless whether you calculate this density of states in terms of the omega variables or in terms of Q variables, right? Okay, so therefore these two should be identical, and we know that dq delta Q is actually proportional to Q squared dq, because that is coming from sum over Q vector in three-dimensional space, and therefore this three-dimensional summation over Q vector is actually 2 pi Q squared dq, right? So for isotropic Brillouin zone, so you could very easily see that this is Q squared dq, because you integrate over three-dimensional Q vector, which is 2 pi Q squared dq, right? Okay, and therefore you know that this must be omega squared, because omega is proportional to Q, and therefore you can combine these two relations, you get omega d omega. Okay, of course you need to figure out this prefactor or this normalization factor, but the qualitative behavior is actually down. Okay, so and that's the origin of the omega square densive states that in this Debye approximation. Okay, so of course in reality the densive states profile may fluctuate, and they may not be exactly described by the red curve, the quadratic densive states, but roughly this quadratic behavior describes very well many realistic materials, because again the low temperature, low energy excitations of phonons are dominated by this acoustic phonons, where you know that they have this absolute value of the sine qa over 2, right? Okay, and so you can linearize this phonon branch in the Q goes 0 limit, and that is precisely the assumption that behind the Debye approximation. And you can see that, of course, this acoustic phonon does not contribute 100% this phonon, the densive states, but they can capture at least 80 or 90% of the densive states profile. And we don't care about this wiggles and this little bit fluctuations, because the only thing that we care is the simple power law behavior of densive states of phonons in relation to these frequencies. But we could fix this normalization factor here by this conservation of the total densive states. As I mentioned, you could determine this d omega is actually a times omega squared d omega. And you know very well that this, for a simple Bravais lattice, the total number of degrees of freedom is 3n. Okay, so you get 3n amount of particle number, or this phonon states, which is the integral over all the densive states from 0 omega to the Debye frequency omega d, and therefore you know what this Debye frequency is. So we may end here today, but let me just make a final remark. So why is there a cutoff? The reason why there is a cutoff is because all these kind of excitations are restricted to this lattice constant A. So all this kind of a momentum or energies of the underlying excitations are restricted to this lattice constant. So lambda, which is any kind of fluctuations or wave-like fluctuations, must be larger than this lattice constant. And therefore, if you inverse this relation, you get the upper bound of this external energies or frequencies, which is inverse of the lattice constant 1 over a, and that is the origin of this Debye cutoff frequency omega d, because this serves as a natural cutoff to all these external energies that could lead to the phonon vibrations. So all these phonon vibrations with the characteristic wavelength lambda, which should be larger than this lattice constant, which is the minima or the lowest length scale you can reach, and inverse of that length scale corresponds to the largest amount of energies or momentum transfer, and this serves as a natural cutoff to the Debye energy and Debye frequency. And you can check different materials show different cutoff because they have different lattice constant. Okay, so I guess that should be enough for today. And next time we will derive this CV based on this Debye approximation, and we will explicitly derive the prefactor in front of this omega square density of states, and that relies on the definition of the Debye temperature, and we will discuss that next time. Well, so now you can appreciate the powerful tool that we learned by second quantizing the Hamiltonian, at least in phonon province. Then you can easily evaluate anything you like based on the second quantized Hamiltonian, and we will continue finishing this next time. Okay, and in the meantime, I suggest that I encourage and I request and I ask, I demand that you read the corresponding chapter and sections in Flansburgh and also in Kittel's second book. Okay, and you can go back to the Kittel's first book on Introduction to Solid State, and read that corresponding chapters again, and you could gain much deeper understanding from the second quantized formalism. Okay, great. So I'll see you on next Monday.